For 3 years, a consortium led by Comat and composed by laboratories like the French National Center for Scientific Research and the Bundeswehr University of Munich, as well as companies like PlasmaSolve, OHB, Thales Alenia Space, have been developing a disruptive electric propulsion system for nanosatellites. Nanosatellites have emerged as a revolutionary class of spacecraft, reshaping the landscape of space exploration. Typically weighing a few kilograms and measuring just a few centimeters, they have gained popularity due to their cost-effectiveness, rapid development cycles, and the ability to accomplish a wide range of missions. They are frequently deployed in constellations, thus enabling enhanced global coverage and applications such as Earth observation or communication, for instance. We believe that the propulsion system is the technology limiting the development of applications on satellites smaller than 12U. Currently, there are no electric propulsion modules powerful enough for both orbital transfer and station keeping. Hence, operators launch their satellites on dedicated launchers, which greatly increases the cost of orbital infrastructure. Our aim was to offer a disruptive technology that is sufficiently versatile to carry out a wide range of missions.
The plasma jetpack technology is a technology of electrical propulsion module for small satellites. The physics used in order to create thrust is the vacuum arc physics. This physics allows to create thrust using solid metal propellant. Applied to space propulsion, this physics allows to have solid metal propellant and to largely simplify the electrical propulsion module. Indeed, it is possible to remove tanks and valves to have a very simple device ready to thrust. The very high speed of ions allow to have very important specific impulse and consequently to store a lot of momentum and very reduced volume. Contrary to gas-feed thruster, it is possible to implement this propulsion module on 12U satellites and to have large amount of propellant and momentum to perform different kinds of missions as orbitalizing, station keeping or deorbitation.
The plasma jetpack is a modular propulsion system. It consists of a box, the PPSCU, containing the thrusters, control and power components. From 1 to 4 nozzles can be connected to the PPSCU, these being the modules that generate the plasma and therefore the thrusts. Energy is stored in capacitors, which are directly connected to the electrodes. When the arc occurs, this energy is used to erode one electrode and to generate thrust. This thruster, with its solid propellant, offers significant advantages in terms of total system volume. It is one of the most compact modules in the world, simplicity, no valves, no pressurization, so no risk of explosion, and safety. The metal is non-toxic, so no handling precautions are needed. The plasma jetpack can be used on demand from 0 to 30 watts without preheating. Its pulse operation generates a precise and controlled thrust for attitude control, station keeping, or deorbiting, for instance. This is one of the most innovative technologies existing. However, behind its ease of use, compactness, and practicality lies the complexity of vacuum arc physics. Our understanding of this phenomena is far from complete, despite the expertise of our consortium members. A great deal of research and work remains to be done to improve performances especially in terms of electrode erosion and hence thruster's life duration. This technology can be used for a wide range of missions, from telecommunication to observation. It will open up new possibilities. Beyond traditional missions, we believe it is possible to master in-flight formation, docking, spying, or boarding operations thanks to the control of the amount of momentum delivered by the pulse thrust of the plasma jetpack technology.
Since we are now at the end of this project, the consortium warmly thanks the European Union for their support and funding through the H2020 program under grant number 870444.